so you can read it up, and there are some of them, like there is this no Python, like there is this no GIL, like there is this cache. So there are various arguments that parallel that you can give to the function to improve its definition. So let's try to use some of them and improve our code of before. So at the moment here we defined numba Laplace here with JIT simply. Okay. Now let's say to give another arguments like no Python. So if you read the documentation, they tell you that these will remove all the Python instruction if possible, otherwise will give you an error. So if it's possible, we remove the Python instruction and we can check its performance by adding it. So let me take it from here. Just a second. Here, this one I want. So we can test it now. So let's name this number2, and I can test it up by putting it, by calling it for this was this is still another example. Sorry, this comes after. Let's put here number2 of x, and I still do the performance plot. So I define it and add it here to the plot. So this is adding, why does it take so much time? Because I'm running 20 times before 4. I should run it less. Anyway, it has run. So what happened here with this number2 where we use no Python, basically compared to the previous one, you see that it's slightly faster. It grows, it's everywhere slightly faster. What it happened now is that those that were left over of Python instruction completely disappeared. So in our function here, we are doing some things like an assertion here, or we are using NumPy, that are instructions that Numba prefers to don't compile, but to make them do by Python. And what will compile is only the for loop. If we say no Python, instead we say to it, okay, do your best and compile everything. And this is what it's going to do, and it's slightly faster everywhere. Not a big improvement, but slightly faster. Another option is to use fastmath. That on my laptop I didn't see any advantage, but let's try here on the nodes. So this is number 3 with fastmath, and I can try to add it here. So let me change the 20 to 4 times. I run it only 4 times, and this is number 3. So this should compile with the flag of the compiler that does fastmath. Here, these are better CPUs than the one of my laptop. So on my laptop, I wouldn't see a difference. Here, you see a difference. So these, we added a more instruction to the compiler and say, look, use fastmath. And so then it does another layer of optimization. Okay, there are many others here that you can check. There is cache equal true that will use the cache, or well, there are others. Another one that is quite interesting is parallel. So for parallel, we need to do something a bit more complicated now. And for running the code in parallel, we should take back our code here. And I can say this is going to be the number Laplace 4, which is parallel. I want to say, now let me use it as a decorator since we're doing it here. So I keep the best we did up to now. If you want to pass flags, you do it in this way. You don't pass the first argument. This is going to be the function after, and the rest is here. And I can say parallel equal true. If I compile it like this, it will tell me an error. At least this is what I got on my laptop. And let me try, but it should give an error if I compile it like this, because it does not know what to parallelize. So just let me try. Yeah, exactly. it's not going to parallelize the code. So it says parallel equal true was specified, but no transformation for parallel execution was possible. So it didn't actually know how to parallelize it, and you see that it's performing like before. Indeed, how do you parallelize these? This is another indication of the fact that JIT did nothing at this level. It didn't check the content of the function or whatever. It just said, okay, thank you for the function. I store it. When you call it the first time, I will think about it. And what we can do here, it's from number import prange. So this means parallel range. And the idea of number is to replace the normal range with a parallel range. Okay, so this is what I do here. And now if I run it, we will not complain anymore, and we run it in parallel. And wow, we are faster. Not everywhere though. Can someone tell me why we are not so faster everywhere? Any idea?
When the size is small, you get larger overheads to split into parallel, so you don't get any faster.
Thank you, Pantelis. Exactly. The problem is that one that when the size is smaller, the running in parallel, this you should see it also with OpenMP. Running in parallel, we have this problem that we are increasing the overheads, and so we are paying more overheads. We don't see the performance up to here, and we see performance only after. Okay, so it's not always optimal to run in parallel. And still we see this picture here. So we are running, we're fitting in the cache, then we go out of the cache and everything falls.
How many threads do we use here?
That's a very good question. And I don't know, not because I don't know by my own, but because Numba doesn't tell us, doesn't let us fix them, and it will choose by its own what is the optimal. So there is no way to fix it. I checked for it. There is no way to fix it. But we can check if we're running actually in parallel by opening a terminal. And here I'm in the node. I can, for instance, so here I'm inside the node where I'm running. I can press, I can say edge top. This will show me the usage of the CPUs. Okay, so these are our 20 CPUs that we have in this node. And when I run it in parallel, what you should see is that at the moment there are not everything is used. When I say to run in parallel, you should see light it up like this. You see that we are using 2, or yeah, also others were involved but with less work. So all of them have involved, but I think actively you can say that 2 have been used. It's a bit difficult to time it well, but this is what you can see, that all of them lighted up. So all of them, they've been invoked. Is this the fastest we can achieve with parallel? When you do things in parallel, you need to be careful, because you may not want, like we said before, parallelize things that maybe are faster to do serially. So here with Numba, we're opening 2 parallel regions, but I saw on my laptop, now I need to see also here, that is better actually to open only 1 parallel region. So this is Numba 5. Okay, so if I open only 1 parallel region instead of 2, this Numba 5 should be faster than Numba 4. But it performs quite similarly. We will see after better. So, but it performs very similarly. Actually, okay, it's maybe a bit slower. Here it's not so bad, so good. But I will show you after a case where it's much better. So this was up to here, up to this example. Now, there are some other indications for speeding up much more this kernel. Okay. And there are other ways to do it in Numba. And I want just to show you a way to get a really huge speed up. And this way is to remove all the possible overheads by defining a function like this one that I'm going to name Numba 6. At the moment, I will not use other flags like fastmath, etc. Well, let's put fastmath, but not parallel at the moment. So let's keep fastmath. And the idea of this one is to don't define out inside the array, but to define it before, and as well to use the trick I used before with the padding. I don't have the module. I will explain you soon why the module is a problem. Now, just this, with -1, +1, etc. So I do something like this, okay? So we want, this is the function I want to define, and the way I'm going to use it is by the same of before, just I define there a padded array like before. So this is incrementing the directions of x. This is a padded array of x, and out is the same dimension of array. So I don't do the shift, etc. I create array and out with the same dimension, just do looping inside the domain. So we add the one on the left and one on the right. We loop less. We access the neighbors, and our result will be in the inner part of out. Okay. So this way, if I'm going to use now number 6, are you ready? What I saw on my case, it's a huge speed up. Look here. So what did just happen? What are we seeing here? So this is a huge speed up over all the range. Okay, even faster than the parallel version. Huge speed up everywhere. Why? There are a number of reasons for this. First of all, we get rid of the overrides. So we are seeing the computational the peak performance. We are reaching peak performance already earlier, and this gives us this kind of picture where we have 1, 2, and 3 jumps. Then this is significantly lower than should be stabilized here. I don't have a good explanation why this is significantly lower, but we see 1, 2, 3 jumps. If you do the math and you check it a bit, these 3 jumps should be equivalent to the size of the L1, L2, and L3 cache. So before I mentioned the cache, in the CPU there are 3 different caches. There is 1, 2, 3, and these are the 3 different sizes of the cache. So this is where it fits up to L1 cache, this is up to L2 cache, and this is L3 cache. Then we are flattening out, and this should continue flattened here. So this is a huge speed up on the low level. We are seeing this huge speed up here, and it's a speed up of order of magnitude compared to before. So now we went to the scale 10 to -9. So before we were even 3 to 10 to -8, here we arrived to 17.5 compared to this. So we are a factor of, I don't know, 6 times faster than this one in this region. For then lowering, but still being faster. Okay. And the reason why this happens is we remove the override, so we see it earlier, and the compiler with such an expression can do a much better job. Why is that? Because we are just incrementing the indexes of decremented or incremented of 1. So the compiler knows that you're just accessing the next neighbor or the earlier neighbor. Okay, it knows that you're accessing those. It's not like before here that we are putting a modulo, and the modulo, the compiler cannot say immediately, okay, this is always the one after accepting the condition where you're at the border. You're asking the compiler too much. So the compiler will not optimize this memory access, and will compute this modulo and then do the memory access. Here instead, you are optimizing all the memory accesses, okay? And the compiler can do a very good job in compiling this. Okay, so this is huge speed up compared to before. This is almost as good as what you will get with a C code. Questions? Okay, so now let's take really the best out of Numba, and so let's do a couple of changes more. I wanted to show you again. Let's add more curves on this function. So let's do again the parallel, and let's put it first in both. Yesterday on my laptop, as I told you, I saw that this should be slower than putting it only on one of them. So let's call, wait a second, this was number 6. This is number 7. So let's put here number 7. And this is now, we should see the same picture of before. Amazing. We have more overheads, but look at the speed up. Now we are here. Still L3 cache, but look, this is a great speed up. And I saw that if I remove the P range from there, so the difference between this and that is without this P range. So this is number 8. You try it out, and this is the 8, and I saw that it should be no, nothing on the here. We don't have the we have more cores, etc. They're better. It's not like my laptop, so there is no difference on having the both P range. So I really saw on my machine that there was still a difference. So I can show you here. This was the results I was getting on my machine, and you see that this number 4 was with double P range. The number 5 is with only 1 P range, and you see there is a speed up still compared to that. Here on Cyclone are better CPUs than mine, and so yeah, it's better. So you don't need actually number 8 and number 5 are the same. You can put in both cases both P range. Okay, so this is really, I think it's the best you can get out of Numba, of pure Numba. Questions? Then now we will change topic, so we leave Numba. This was, I've quite exhausted the topic. We took today a function, I cannot compare it here, but we started from an implementation of this morning that was terrible, and we arrived here. So we look at the levels. Arrived to.
Can you just show the log scale of this?
Yeah,
just
sure.
To see,
sure.
Here.
It's thank you for asking. Yeah, you see the log scale, it's always quite difficult. So there are regions where some of them have smaller overheads, more, and here it's, yeah, neither the log scale does always a good job. Okay.
Okay, thanks.
So just to summarize, because we've done many alterations on
Panayota, sorry, can you speak closer to the microphone? Or
no?
Yeah, it was quite low, the sound. Go ahead.
So, yeah, can you
yeah, it's better now.
Can you summarize so kind of rule of thumbs for this kind of thing? So use Numba and use JIT.
Yeah, okay. Yeah, of course. Exactly, yes. Let's say the idea behind Numba is to accelerate function by keeping your code simple. So JIT is the only way. You can also pre-compile, but the best, you can pre-compile by defining the arguments the function will have. So if you don't want to use just in time because you want to save some costs, you need to do like it is, define the arguments of the function, what gives and what returns. So if you don't want to use JIT, you need to define the input and output of it. But in general, a suggestion is to use JIT to check for flags. So you should do always this kind of exercise. Try various, if it's okay, the rule of thumb is always that take the most expensive part of your code. Never do this never waste a lot of time on doing this everywhere. So use a profiling, and if you are fitting a function or whatever, you have a kernel that is called thousands of times, and it's the critical component for your performance, and it's written in Python, then try to use Numba. This is one first rule of thumb. Second rule of thumb is try it out in many ways like I did today. It costs a bit of time, but you always do the scaling over a long region. Never focus on the, like we saw here, never focus on where the overheads are. So always scale it up, the code. Never check, here I got already a speed up of 3. Yeah, but then maybe the speed up of 3, it's nothing when you go at the real size you want to run. So always check on big sizes your code, never on small one, because otherwise the overheads fool yourself. So always go here in this region. Then compare different implementation and choose the optimal one for your code. So take one piece of code that you want to optimize, try it different times, try different implementation, and take the best one. Numba works excellently with simple kernels. Now, don't try to use it on very complicated function that call other function, etc., because then, yeah, it gets complicated. So there might be parts that don't compile, etc. So Numba works excellently with simple kernels. And this is how you should divide your code. So if you have many kernels that you need to run, so let's say you have a kernel 1, a kernel 2, a kernel 3, and then you have a function that it's a master, a main function, that will call according to the cases or use this kernel. So suppose you have a main function that then will call kernel 1, then you have another for loop, and it calls kernel 2, etc. So if you have a main function that is using the various kernel, what you should not optimize is not JIT this function, but JIT the single kernels. Okay, so this is another rule of thumb. And yeah, like I said, take the profile, the slowest one, and try to optimize it. It works excellently with the simple cases. You make it more complex, start to get errors. So keep it simple, and it will work fine.
I also have a question in your very last comment, if that's all right.
Yeah.
Which is in the very bottom of what you were just typing with the 3 different kernel examples, like a toy case there.
Yeah.
So you said, so we would pre-compile kernel 2 and then put it inside a for loop. So isn't the for loop itself costly in simple in vanilla Python?
Yeah, of course. When I mean for loop, I never mean a for loop over the data, but
small, like few iterations. You mean probably
few iterations that maybe like before I did the for loop over the number of dimensions. So
yes.
Okay, so
Thanks,
it's never. Yes, the main rule of thumb that I wrote here, and that is the most important rule of thumb. Never do for loops on data in Python. Never, ever. That's use always something else.
Thanks.
That is already a speed up of 3 orders of magnitude. Then everything else, it's something. It's optimization. Okay.
Although this JIT is now we are in interactive mode. When we are doing Slurm scripts, is there a way to?
Yeah, it's not a problem. The fact that it's interactive, the fact that it's just in time and we are using interactive does not mean you cannot use it in script. This can be simply a function you define in your script and you submit it. Then at the moment you run it, the Numba will compile it. So we call a compiler and run it. I mean, at the moment here, like I opened before a terminal, just to make you understand, we're already on a working node, so we are compiling it. Of course, it's a big overhead, the compilation, that maybe if you have running in parallel, then you have 10 Python scripts that are all compiling the code, but are minimal overheads, are a setup cost that is not going to affect you. And if these affect you really, then you can pre-compile it and read how to pre-compile codes, but it should never affect you.
Okay, thanks.
Can you pre-compile a function that has a pre-compiled function within?
Yeah, okay, on this, let me rephrase your question. Anything that is compiled that is a C code like NumPy before, unless Numba knows how to map it in a C code, unless it knows how to do it, it will not compile it otherwise, and we'll just call it. So we'll have some Python limitations, some Python regions, that if you put the no Python region, then it will throw you errors. If you put the flag no Python equal to, will throw you error if it cannot map it. Otherwise, you can have some Python region inside that is not a problem as far as they are not the critical component of your code. So NumPy here will not NumPy will not compile NumPy or whatever other function, complicated function you call. It will just call it like Python would do. Okay, so even if you call a precompiled function inside a precompiled function, it's not a problem. NumPy will say, okay, I don't touch this line, I just call it, etc. The important is that it can compile all the for loops. So the for loops are simple. Then here I can put something complicated that does not want to compile and will not compile it.
Okay, thanks. But here I'm a bit confused. Here we use no Python. Equals to, but here we use the argument no Python. So how did it compile the NumPy?
Because it knows it can map some function. That is fine.
Okay, okay.
It knows NumPy is well known, so it knows how to map NumPy.
Okay.
If it's something else it does not know it.
Okay,
yeah.
Thanks.
Okay, so I hope you enjoyed the part of NumPy. Now let's go on other technical. This is another package that I really love, and it's quite new, and I suppose nobody of you ever used it, but it will be, I think it's a great package. And let me create a new cell and start a new topic that is connected. We are continuing with this, but it's another way of doing things, and its name is CPPYY. So this is a package that quite new, like I said. It's a significant effort. I've also contributed to it, and it's very, very nice. And the idea here is to automatically creating Python bindings for C++. So it might look complicated because we are going back to the C and not really Python, but it's something that, yeah, if you're doing HPC, you need to know anyway a small knowledge of C or C++. So that's the idea here. And what it does, this package is, okay, let me zoom in. Just a second. This package is named on the compiler that is CLang. It's another compiler in C, and it's based on CLing, that is based on CLang, etc. And the idea here is to either just-in-time compile C code. So with this cppy.cppdef, one can pass some C code and define it. Then you get a function that you can directly access from Python. Okay, this is one usage case. Another usage case that is very nice is of simply including, use it as a C compiler. So you include an header of a library. You load the library itself that should be stored as a shared library. This we will see it after better. And then you can just call directly functions from this library. Okay, so these are two different usage cases. I will start with the first, and then we started at 15. I don't know if there is time to do everything. Maybe later we go to the second. But yeah, this is a great package, and if you want to try to use it in your project, I think you gain a lot. Especially if you have on the other side a C or C++ code that you want to interface to. So the idea, what is it? Well, you can compile it via pip. That I already installed it. Sorry, the package you can install it via pip. You can try it out. It's here with mine. It's already installed. By the way, let me do this parenthesis after. Just it's fine. That is how to use Python actually on Cyclone. So I didn't actually explain you how to use Python on Cyclone. I prepared everything, so that I will say it afterwards. But now let's go first on CPPYY. The first approach is to use cppdef. So I want to define a function. Let's not include the studio.h that is already included, I think. It should not have problems. And how you will define our last implementation, this one, here in C. So this one, let me copy, don't want to close it. Let me copy this and paste it here just to make you see it. So how you will define the same function in C, it's in this way. You take an array of input that is R, a double array. Let's suppose that is double. So you see in C we need to specify all the types. So this is a double array that is our input, R. There is a double array that is our output, out. Then we need to know in C what is going to be the size of the array. So we need to pass explicitly X and Y, because these are just double pointers. And so you cannot know from it what is going to be the size of the array. So this is something you will do in C. You pass the size of the two arrays. And then we loop in the same way that we do here with the range 1x minus 1. We do a for loop of x equal 1 to x capital minus 1, x plus plus, y loop. And then if we want to access the data, these are single pointers. This is how the data are actually stored in memory, even in NumPy. And so if we want to access the component x and y, we need to use a small trick and unpack the indexes. And so to multiply x times the size of y and add y. So this is actually, y here is the running faster index. So we have inside for every x, we have inside the y. So, I mean, this should be clear if you do mp.arrange and you suppose you say 10,10, doesn't like, what doesn't like? I think maybe arrange doesn't use shape. I thought nothing. We cannot use arrange. Let's use a random. And let's say that is a matrix of size. Let's make it simpler, 4 times 4. Also, random does not want a tuple. Now, this is a matrix of size 4. So the component, the inner index is the faster running index, 0, 1, 2, 3. And then it continues 4, 5, 6, 7, 8, 9, 10, etc. And these are, it's actually how it's stored in memory. It's in a flattened approach that in memory, this array, even if it has a shape 4 times 4, it's actually stored like flattened, like this. So all of them are in a sequence. All right. So when this is actually how it's stored in memory. Just NumPy knows that every 4 it needs to, that this instruction here means actually doing this. So we multiply times the size of y, x times the size of y plus y. And this is how I'm mapping all the indexes. So it's x minus 1 times y, x plus 1 times y minus 1, y plus 1, x and y. Okay, so this is how you would write this function in C. All right. Now,
can I ask something?
Yeah, sure.
How does the compiler knows what memory to allocate, or does it allocate in the
start? No, that's indeed that's a good question, and it does not. It does not, and you need to always be careful and compile something that actually compiles. So with this, in this way, you can obtain segmentation faults. So I don't want to crash this notebook. Let me open a new one. No, CPPY, the point of C in general is that it does not have any barrier, any control. So any error management. So while Python does all of that for you, and if you try to access like we did before, a component that is out of range will tell you, no, look, it's out of range. C will never check for that. So if I define this one here now, okay, and I call it like I want to call it. So let's define, let's define this. So I define X out, and I call this one, I'm going to call it like this, and say cppyy.gbl. So GBL is the global space where all the functions are defined. So you can check this in the documentation. When you want to access something, you do .gbl. And then you find the function name. So here I'm going to find since I compiled it, I'm going to find a Laplace here. And this is basically a overloaded function. Well, this is how it names it. It's this function. Okay, that now I can call. I can call maybe with 1, 2, and it will tell me, wait, Laplace takes 4 arguments and you just gave 2. So if I called it wrong, CPPY does for us this check, but it will never check that the array you give me, it's actually correct for what I'm doing. So if now I call it in the wrong way, okay, so this is a reason why Numba is better, because Numba also will do the check for you. It's still in Python. Numba knows what array you give and knows that if you are going out of the range. So Numba will do these checks for you. CPPY will not. And so if here now I call array the input out, and then I give size comma size, let's say size comma size. Just a second, size equal 10. This one, NumPy is not defined, of course. This one, it has worked now because I called it in the correct way. I didn't do anything wrong. But suppose I say the size of one is 2 times larger. This is something that in C will bring you to a segmentation fault, because I'm going out of memory. So you all know, I think everyone that ever programmed in C knows what a segmentation fault is. And you are going out of memory. And this is going to happen here as well. So this is why I didn't want to run it there, because this is going to make crash my notebook. Sorry, it should have crashed, but didn't say something. No, it didn't crash. Okay, now it crashed, I suppose. You see, it's restarting, and now I got errors that I didn't see there because it's running live. Errors that though appeared in my notebook now, that basically a segmentation fault happened. So here I got errors, and that one is crashed. So of course you can run in this approach when you use pure C and you don't put barriers, you can run in segmentation faults again. Okay, so it does not save you from that. It cannot do magic. Okay.
Okay, thanks.
Hopefully now the notebook here didn't crash, so this one should be still up. Yeah, perfect. So let's forget that. Now we defined Laplace and we are going to call it. All right. Now we are going to use, where am I? It's not this one, sorry, this one here. We're going to call it, and so basically define the function, and now I'm going to check its timing. So I'm going to call CPPY HBL Laplace, and now like the only difference with respect to what we were doing before is that we need to explicitly say X and Y. Okay, so I compile it. I run, so this already compiled it. I run it, and this is it here. It performs as good almost as non-parallel version of Numba. So it's not parallel now, right? So we should remove these other two, but it's this line here. So we're using pure C. So Numba, this tells us that Numba already did a very good job. Okay. So it's not that, I mean, CPPY is an alternative for another reason, for the fact that it allows you to automatically interface to C code. So it's much more powerful than Numba itself. And now I'm going to give you some more examples. But is it clear what happened now? So CPPY did automatically the conversion of the array input here. So yeah, there is a lot, actually there is really a lot under the hoods here. So CPY did automatically the conversion of a NumPy array, so it knows how to convert a NumPy array to a C pointer. Basically, it passed the pointer of the array. You can see this if you do, I don't remember right now, array dot, should be data. Anyway, this is the pointer of the memory. So the data of the array are stored in this pointer. CPY has accessed that and gave it here. It checked like before for the number of arguments and checked also for the type of the array. So here we are saying that it's double, and this array is actually double. But if I try to run the same for an array that is integer, it will it will give us an error. So suppose this one, I say now that the D type is equal float 32. Now it will give us an error, not because of that. This is random. Why didn't I like the type? Sorry, let's convert it. I can say dot as type. Yeah, now this is the error I wanted to look, and it's telling me that it could not convert argument 1 to double pointer, because actually is a float pointer in memory. So it's also protecting us from that. Okay, so CPY is doing some work for us, and it's automatically binding, doing the Python binding and converting arguments. All right. I mean, this is something, needs some trials, but you can, by the way, there was a question regarding, there is a question from Angros, maybe I check it after, because we have 15 minutes left now before the break. Yeah, so let's plot it again here. And yeah, CPY is really, really powerful, needs some bit of understanding, but it works very well for this, also here, most of the cases. And now let's show you another usage of this package. And it's the usage that I mentioned before, when you want to, that is actually the main purpose of this package, that is to produce automatic Python and C++ bindings. And how does this happen? So how does it happen? For doing this, let's go now a bit more practical on the terminal. And I'm going to do it here for you. Let me create a dir, make up a dir cppyy. Okay, and I'm going to create here a code. So what do we need usually when we want to do a C package? So we want to have a C file, okay. Emacs, now I cannot use it like this. Okay, let me touch this. I suppose that if I touch it, I go here, because we're in a computing node, so Emacs is not available, but I can still edit it. So I edit it from here. So sorry, at the moment, spoiler alert, we're going to use OpenMP soon. Let's comment it out for now. So this is the minimal structure you need to give to this, to a C file, for being able to compile this code. As I told you before, the CPY would have already imported Studio.h, but if you want to compile this with GCC, you need to include Studio.h and then the file. Okay, so this is our file, and we can simply say now GCC -c, and then we can put some optimization, suppose -03, and then we can say Laplace.c. What did it happen? Now we created a Laplace.o, right? So this, I think you saw it yesterday. If you compile a C file, you get Laplace.o. Now this Laplace.o is the compiler now has translated the content of Laplace.c in in a machine code in a machine code instruction, a set of machine code is machine instructions, and this is a compiled code. And now what we can do now, for instance, and actually what we have to do, because this is if you want to make this a library, you need to make it you need to pack it in a library. So usually there are two kinds of libraries. Let me how to do this. So when you let's do this. If I do module available, this we will use it also after. We will see the list of modules available. For instance, between these modules, there is OpenBLAS, that is a common BLAS is a set of basic linear algebra routine. So the BLAS, where is it? OpenBLAS? Yeah, BLAS means basic linear algebra subroutines. OpenBLAS, this is a standard like yesterday, MPI, this is a standard as well. And OpenBLAS, like OpenMPI, is an implementation of this standard that is open source. You have other BLAS implementation, but this is a standard. OpenBLAS is the implementation, is the library. And so when, if we load, if now I do module show OpenBLAS, what you see here is basically what the module load will do when you want to load OpenBLAS. So when you want to load OpenBLAS, we'll change these environment variables. These are named environment variables. We'll append to this one these values here. Okay, so when I load it, we'll append this one. And for instance, LD library path is where the compiler looks for libraries. And inside here, then, if I do ls of this directory here, we have, it's actually where the module is compiled, and it's where we have the libraries. The libraries usually come in two ways, in .a and .so. .a is a static library. .so is a shared library. Okay. .a, it's something you need to include a compile time and will be fixed, because the compiler will basically copy piece of inside this code in the other. So we'll copy only what is needed. So if I now I do du -h of this one, of this library here, sorry, this is just a link. I do of the, you see that is in blue, just a link. This is actually the real library. If I do the du -h, this is 11 megabyte. Okay. But when we compile linking to this library, if you do it statically, the compiler will not copy 11 megabytes of information in your executable, but will only copy from the .a what is needed. So BLAS implements many of these things, many of these functions. These are, you can say, see the list of namespace by using nm. So if I do this, you can see that inside this object there are all these functions. So this is a function of BLAS. There are many others, etc. And when you compile with link into a .a file, the compiler will copy the set of instruction there in your code. Instead, the shared object, this one, it's a more modern way. So this is an old way of doing this. Also some more efficient under some point of views. But the modern way, since the library may change. So if the library gets updated and you don't want to recompile the code. So the issue here, you see it. When I compile it statically, this will be forever inside my executable. So I compile an executable and forever have this set of instructions. But maybe there is a bug, something else. If the system administrators update the .so file, automatically your executable will use the new file when you are linking to it. So this you can see it, for instance, let me take, I don't know if I don't think I have something in my home. Okay, let me see a second here. If I do LDD of this object, no, this does not work. Anyway, we LDD usually, if you do it against an executable, now you need to find a good executable, you will see the list of shared libraries that is linking to. So I don't have something on my home. Maybe if you do it against some examples of yesterday, you should see that that's the case. Suppose, okay, I do LDD, but would it work? So if I say which Python, okay, let's do this. This is the executable of Python. If I do LDD of this one, you see that these are the shared libraries that we are pointing to and how they're resolved. So this is the name of the shared library. This is where it's taken. Okay. Shared library are loaded dynamically, and this is what you want to use when you use Python. So when you use Python, you want to compile, especially CPY, but in general for any linkage of libraries, since you don't want to link them at compile time, because that would mean linking them when you compile Python itself, you want to compile the code as a shared library, and then you can load it in. So when CPY is giving you this opportunity here of loading a library, we look for a shared library. I try to make it clear that what the difference between shared and static library. Now we'll tell you how to create a shared library. But yeah, questions? Yeah, I know. Maybe you're confused or understood everything, one of the two, I suppose, but let's proceed. Let's go ahead. So now I've created this, I've compiled in this directory the Laplace.o. At the moment, I didn't do it in the correct way because I compiled it statically. For compiled in a correct way for a shared library, you need to add -fpic. This will add some more layers on the compilation. So with you compile your source code with -fpic. You can look online anyway how to make something shared. There are many ways, but in general, if you use an external library, all of them, they have a shared library like I showed you for OpenBLAS. And then once you have a list of .o file, you can collect all of them by writing GCC -shared. This is the output, the .so. Okay. And after you put all the files .o to be collected inside this shared object. So if I do this, now I have this .so. Now I put here in the README how to do this. Sorry. So after you can have it, can you refresh this? So here in the README, I put these two instructions, so you have them. Now, okay, so these are the two instructions I used for creating the .so file. Now we have the .so file. What we need still is an header file. So inside this .so, there is no information on how the function is actually defined. So what is the signature of the function? Here you have it written, but usually when you, in the .so, this is not collected. So this is also the reason why header files exist, because you need to know, you need to bring, to be able to have the smallest amount of information on what is, what your files of what the library, whatever contains, for them being able to use it somewhere else. So usually what you do, it's like, not Emacs, let me touch. It's to create a .h file. And like here, we have Laplace.c. This is a companion that we didn't need now for compiling. So this one, if you see here, it's usually correct to, usually when you do these things, they tell you also to include in Laplace.c the header file. So you should use also here, include Laplace.h. Okay, it wasn't needed at the moment, so just to check the compiles, it should compile. It wasn't needed at the moment because we don't need to say what Laplace.age is. It already knows it. But usually this is done because if you do a mistake, a change of the arguments, like this, I changed this to float, the compiler then will complain and will tell you, look, in the header file, this is name float, but now we are writing a double. So this is why usually they tell you when you write something to include also the .age file. Okay, but it's not needed to put the signature for the compilation itself. Sorry. It's not needed. Okay, so let's recompile it and let's make this shared. Now, this is a shared library that in another executable, we can then link it to, and in the same time, load the .age file, and then we will use the content of it. Questions? So this is what you will do in pure C. And now what, okay, we have the same name. This is going to be a problem. Let me rename it here now as Laplace2, Laplace2. And let me recompile, just because I already defined something named Laplace. So did I save it? Sorry. Just because I already defined something named Laplace here in CPPY. And the idea now is to use CPPY.C include to load the Laplace.age. So this we have it inside, I created a directory CPPY, so we have it in the directory. You need to put here a path. So CPPYY / Laplace.age. So this should run true. It has read this file. Okay. Now we have defined a Laplace.2. So if I say CPPY.gbl, I have a Laplace2 because it's coming from reading this header file. So you see, this is very powerful. You have a library, you load the header file, you get the function, and now theoretically you can call it. Can I? Am I going to have troubles? Let's see. If I CPPY2 Laplace2, I'm going to have troubles. Oh, no, did it crash? Sorry, something bad happened here. Yeah, anyway, I should have troubles because I didn't load the library. So I hope I didn't make it crash. What you need to do also is to load library and load the lib laplace.so that we created there. Okay, so now it should run without, because I received a lot of errors on my left, just now it should run without errors. And we have this new function here that the compiler has compiled. Looks like it's performing even less better than this one. So you see it here. But this is compiled by the compiler, by GCC. Okay, a priori. Now, it's time for a break. Then I will show you a few more things. It's a simple example. Maybe you can do it. Okay. During this break, let's do this. Try what I did here with CPPY, or better, compile a case where I used Pragma OpenMP. So actually the solution is already here. You can comment this, you compile it, and you try to run with the parallel OpenMP now, with the C OpenMP.
Can I ask?
Yes.
How did we compile the function using CPPY def?
We didn't. CPPY did it for us. So it's connected under the Ultra compiler and to this C-Link compiler, okay. And he does it for us.
So if we want to use a specific compiler, then we have to do it the other way.
Of course, and that's usually how you will do it. I mean, this CPP def, it's actually doing something like include is doing. So it's only looking for it's parsing the code, and if it's needed, it compiles it. Otherwise, it's just parsing it. But yeah, it's not.
Yeah, because you are passing a string there.
Yeah, I'm passing the content of, like, it will be this content here.
Okay.
Okay. So yeah, I'm passing this. It's a string that the compiler will compile. Will read and compile. So it's like when it loads Laplace.h, it loads it as a string and pass it through CPP def.
Okay.
So there was a question of Angelos Violaris. He asked regarding not looping over data in Python, is the following example used in the code not consider looping over the data? Yeah, it is. That is looping over the data. Just that at the moment you compile it, if you do it in pure Python, like if that you do it in pure Python without the JIT now. So this was the question of Angelos on Slack. If you do it without the JIT, is looping over data in Python. If you do it with JIT instead, JIT is compiling what the instruction you gave here, and then this looping over data will not be done by Python anymore, but you see at the speed up, it's done by C. So all of this becomes a C code like we are doing now. So it's doing the work for us. It's translating instruction and doing the work for us. Does that reply, Angelos? Yeah, okay. So let's have a break. And yeah, sorry, I've eaten 5 minutes again of the break, but we really need to start on time because then we have there is the seminar. So
Thank you, Simone. So let's everyone please, we start again at 2:45. So let's be on time. Thank you.